So, hello everyone. I'm Panagiotis Fiskilis, and today we're going to talk about EDR evasion for fun and profit. Well, it's mostly about profit at the end of the day, right? I think so. So, some information about me. I am a senior penetration tester with quite some good red teaming experience at Enviso. I have some industry-leading certifications, including OSCP, EWPT, CRTO, and currently I'm going through OSWA and OSWP. They're still on the bakery, working on them. Up next, we have some, as previously mentioned, industry-leading trainings, including Maldev Academy, Anti-Siphon Training, or Black Hills, Altered Security, or Pen Tester Academy, for those who know. And finally, Sector 7. We're mostly going to use Maldev Academy and Sector 7 content in the current presentation. A small note, we're going to use the Holy Bible of EDR evasion, the Evading EDR books from Matt Hand. Personally, I think that's the best cybersecurity book that exists right now. Until Chris releases her books, it will be the second best. Let's have a look in our agenda. First things first, we're going to talk about EDR internals, how a Windows system boots when we have an EDR. Then we're going to talk about hookings. It will be our main pain point and the main evasion point. Then we have EDRs and ETW, how EDRs communicate with ETW, and how we're going to bypass both of them in the next content, EDR and ETW. And finally, we have some, cute fun facts that I thought they were kind of cool regarding EDRs. Let's start. First things first, how an EDR works. Do we all know, what is an EDR? Ooh, nice. Okay, this is going to be fun. So, some more hard parts of the EDR. We have the sensor, the agent, the cloud console or SIEM, and finally we have the human factor, which is the analyst. Let's talk about the sensor. A sensor is basically a service running on Windows when basically the user starts to log in and does some userland things. The sensor, the thing that does is basically consume logs, read logs from fucking everywhere. Then the sensor sends them to the agent, also running on the endpoint. The endpoint can be like a server, a laptop, a desktop, or generally a system that has an EDR attached to it. The agent does some correlations and may trigger some low-hanging fruit alerts, for example, default CobbleStrike beacon. The agent gathers all the information, the telemetry, and sends them to the cloud console and the SIEM. Finally, we have the analyst who flags information as non-issue, true attacks, false positives, etc. Now, way too many technical issues today. I don't know why. So let's talk about the more soft parts of an EDR. We will only talk about 3 of them. There are multiple. We have detections, hookings, and telemetry. Detections are basically the rules. We will focus on detections a bit later, where we will talk about brittle and robust, also mentioned on the EDR evasion book. As I said, best cybersecurity book ever. Then we have the hookings that the EDR puts on some functions, system calls in general. And finally, we have telemetry, which is basically just a simple value that says, okay, we have an alert. There is a threshold for telemetry. If that threshold is passed, we have an alert. Let's talk about brittle and robust detections. I think it's a very nice touch from the book, from Matt Hand's book. Brittle detections are more casual detections. They're mostly signature-based, entropy-based, and generally hash-based. something that also an antivirus can do. But the cool part of the EDR is the robust detection. The robust detections are the dynamic detections or the behavioral detections. It also includes memory scanning. What do we mean when we say behavioral detection? If we have an application that for some reason opens Notepad and Notepad starts talking with the internet, okay, it's weird. Something goes wrong. This behavior can be flagged by an EDR with a dynamic or behavioral detection. You can basically write something like a playbook for your EDR to catch this type of behavior. Then, let's see the EDR execution. We have the kernel driver in ring 1. Back in the day, this could be ring 0, but there were some changes from Microsoft for kernel patching that we're going to see later. Then, when we have the driver initialized for the EDR, we have the next step that starts the EDR service. The EDR service includes both the sensors. There could be multiple sensors, for example, for multiple log sources, and mostly one agent per EDR instance. Finally, we have the Cloud Console, where the agent, as we already mentioned, sends information regarding issues, correlations, etc. And the best and worst part of the EDR world is when we have the user processes, because the entire package, if we can say, well, basically the driver does it, injects the EDR DLL on every user process, which means that every user process is controlled by the EDR. Yes, this includes our malware. So I have some examples here. I have installed CrowdStrike Falcon sensor on a personal home lab that I had. As you can see, we can see the CrowdStrike Falcon driver. A smaller remark, this talk is not specific to CrowdStrike. It's generic. I chose CrowdStrike because it was hot after the CrowdStrike generic incident that happened. I think that we all remember that. As we can see, we see the CrowdStrike driver. Next, we have the Falcon sensor, which is basically the sensor that CrowdStrike uses in order to communicate with agents, SIEMs, etc. Once again, the Falcon sensor from CrowdStrike in a different view of, I think it's Process Hacker, and the service for the EDR. Basically, the EDR service includes both the agent and the sensor, as we have already mentioned. Let's see how we are able to boot a Windows system with an EDR attached. First things first, we have the bootloader. No OS there, we don't know what an EDR is, we don't have Windows, we don't have Linux, we don't have anything. It's basically the base bootloader. Then, we have the bootloader fetching the init function for the kernel initialization. And indeed, we have the kernel initialization process for, let's say, Windows, because this talk focuses only on Windows EDR evasion. Then we have the EDR driver initialization and at the same time the OS initialization. Most drivers start at the same time almost with the operating system, Windows in our case. Then we have the active EDR driver and also active EDR service that can interact with the operating system because, as you can see here, the operating system has already initialized. Next, we have the system initialization, or like the system processes and processes that Windows uses and run as anti-authority system are started, initialized, and they do the things they do. It also includes Windows updates. Then we have the user who logs in and starts spawning user processes in the userland ring 3. And finally, the EDR driver once again injects the EDR DLL on every single process or service, including our malware. Let's talk about hookings. We have basically three main types of hookings. We have the inline API hookings, Basically, it's the most known type of hookings. We're going to talk about C and C++ functions, so we're also going to talk about Windows native API and Windows API. Basically, Windows API is an abstraction of the native API. What do we mean with inline API hooking? For example, when we call from our malware, in our case, a function such as virtualalloc on or anti-allocate virtual memory, which is like the equivalent for native API, the EDR will have it hooked. The EDR will view like the function call, and then we have a hook. Next, we have the import address table hookings. It's basically for the EDR to hook NTDLL and prevent arbitrary functions and general calls from NTDLL from being executed around right and left. Finally, we have an older technique, which is the SSDT hooking, System Service Descriptor Table hooking. I managed to say it correctly. Nice. Basically, SSDT hooking is literally hooking on the kernel. You hook syscalls when you are an EDR. Now, this technique cannot be used because Microsoft has introduced patchcard, because earlier versions of Windows didn't have patchcard and EDR were like quote-unquote free to patch the Windows kernel to place their hooks. Let's see an example of a process, for example, notepad.exe, running with an EDR and without an EDR. First things first, we're going to talk about notepad running without an EDR. We have notepad.exe running normally, then we have the create file W call from kernel 32. Then we have the kernel base API call. Basically, create file W is an abstraction of the function with the same name from kernel base. We prefer using more high-level functions when we write, for example, C or C++ code, because it makes our life like way, way easier. And the last step before we go to the low-level chaos is the end-create file, which is stored on NTDLL. As a small note, all like these calls are on ring 3, as you can see. Ring 3 is the user land, is where the user processes, the user files, everything lives. And then we have the ring 0 chaos. Next. So in general, when we perform a native API call in Windows, we will use these 4 golden instructions. These 4 golden instructions, we're also going to use them later when we develop our malware. What are we doing? We basically store RCX to R10, nothing special, put the SSN, the service number of the syscall on EAX, call syscall, return to normal flow. Easy, right? I think so. And then we have SSDT that takes the number from EAX and actually checks in which syscall it goes. And okay, we have the completion of the syscall with Notepad, for example, to create a file. Let's get on the EDR chaos now. And also in this part, I really hope that you will understand what a hooking is, basically from that cute image right there. Once again, we have notepad.exe, our favorite process, favorite for malware, favorite for reverse engineering. I fucking love Notepad. Why not? So, once again, we have the kernel 32 DLL being executed, and in our example, the EDR has placed a hook on the NTDLL only, not on the kernel-based DLL. We want to call the native API function NTWrite file. What do you think? When we have an EDR and we have a hook, will we be able directly to call that function? Yes or no? I heard someone say yes. Okay. The correct answer is no, by the way. What an EDR hook does. Basically, when we place an EDR hook somewhere, not us, the EDR, and the quote-unquote bad guys that don't want our malware to be executed, for us red teamers, the blue team are very bad guys. Basically, when we try to call such function, the EDR will place the hook, it's like a breakpoint, and then the system will not redirect us to the actual function call on NTDLL, kernel base, or whatever DLL. It will redirect us to the EDR. The EDR then will check all the parameters of the function and be like, okay, what has executed previously? Okay, this, and this. What are the parameters? Okay, for example, for virtual alloc, okay, I see a large buffer, I see weird permissions, RWX, that's malware. And then the EDR can either literally kill the process and all its children, or it can allow the execution. We hopefully want to allow execution even if the EDR detects something weird or anomalous. If we manage to pass the EDR check, it's basically the same thing. We have the execution of the system call, SSTT, and finally the completion of the syscall. Sounds good, right? Now, let's talk for another pain point, EDRs and ETW. Do we know what ETW is? Okay. So, EDRs communicate with ETW. Many EDRs, especially the Microsoft ones, for example, ATP, prefer to use ETW and partially some hookings. For example, if we want to go more deep dive and technical, CrowdStrike uses mostly hooks everywhere. ATP uses hooks on some specific NTDLL functions and relies mostly on ETW. That's why it's a big pain point to bypass ETW when you deal with ATP. So, the EDR will communicate with ETW via kernel drivers. We know it, right? Using two types of function calls, callbacks and notifications. For this talk, you don't need to know what a notification or a callback is. We're going to talk a bit about callbacks later, but not something special. It will be a nice remark, let's say. Let's have an example. ETW will call the EDR when something happens. That something can be an object creation, for example, a file. Could be a new connection to the internet via conhost.exe, for example. A new handle is created, especially handles. EDR love and hate at the same time handles, especially if they are on NTDLL. And ETW will call the EDR to investigate the event of the creation, deletion, etc. So, about callbacks. I promise that it will be kind of short, because it's not that important for us. We are going to talk, we could talk for callbacks and callback hacking in another conference or something, because it's an advanced type of attack. There are two callbacks. They are pre-operation, post-operation. Post-operation are basically, we wait the malware to execute and then we investigate. That's wrong. Modern EDRs use pre-operation callbacks, where basically if we want to step on a function, on NTDLL for example, the EDR will say stop, we investigate, and then you run. Now, we have seen how an EDR works. We have seen everything. Not really everything, but still we have a nice background. Let's break some EDRs. It will be fun, I promise. So, these are the main evasion techniques. We have EDR unhooking, which is a very broad category. The most known technique there is DLL refresh for NTDLL mostly. That's our main pain point, NTDLL. We have direct, indirect syscalls. We have dynamic syscall resolution, for example, with syswhispers. Do we all know syswhispers? Nice. We have debugging with SEAIDs, or Structure Exception Handler, and VEAIDs, Virtual Exception Handler, where it's basically software breakpoints. Then we have the hardware breakpoints, which, trust me, it's way stronger and way more evasive than software breakpoints. And finally, we have the cool ways to bypass ETW. First things first, DLL refresh for NTDLL because that's what we want to have, right? Here, for example, is, there is our malware in memory. We have a copy of NTDLL in memory, but what's the problem? It's hooked. We can't directly access NTDLL. We're going to access the EDR and then NTDLL. So what we're going to do? Well, basically, we will create a new process in suspended mode, so the EDR does not apply hookings or uses ETW to gather information because it is suspended. It will just spend resources if it plays hookings. We will create a suspended process, and then the refresh part, we're going to overwrite the copy of NTDLL from the suspended process. And then we have a clean copy, literally from the disk, no hookings, no breakpoints, no debugging, just plain NTDLL. In some EDRs it may work, in others it may not, because it's a very known technique, and it also requires us to open a handle at the end of the day to NTDLL. Damn. Let's say, for example, we have some practical examples here where we basically I'll be fast, I promise. We basically create a handle to NTDLL, read NTDLL from the disk, and then we literally copy all the headers and information and all sections from NTDLL to us. The talk will probably be on YouTube, so I'm not going to explain every single line of code. You can just rewatch it later at your own pace. Also, you can find multiple websites that use not the exact same code, some paradigm of this code for this specific technique, the DLL refresh. Then we have software debugging, basically, with structured and virtual exception handler. We put some software breakpoints on our malware, and we basically check the next address. It's not that evasive, and it also can be circumvented by the EDR. An EDR has full control over our malware and can basically delete breakpoints for fun, I guess. Now, the hardware breakpoints. Actually, that's a quite new technique. I think it started on late 2024, early 2025 or something. Let's see. We have our normal malware flow where we, for example, allocate some memory or get our variables ready, include our shell code from a header file, nothing special. Or calculate sizes, right? Nothing too spooky for the EDR. Next, we check if the imported function is hooked. We basically can check the original address of NTDLL and compare it to the address of the EDR. Or a way easier way is to we can get the address of the EDR, and if we see an address that looks like an EDR address, it is an EDR address. What are we going to do next? Is use the DR7 register with the instruction int3 or cc in hex and place basically a breakpoint. It is a hardware breakpoint and it cannot be circumvented. Now, later, I'm not sure. Then we're going to find an unhooked version of the NTDLL DLL, for example, with DLL refresh or any other technique that we want to use. And finally, we're going to replace RIP, the instruction pointer, with the address of the unhooked address from the new NTDLL. And finally, we have function execution as intended. And this method actually is way too evasive, and it will do such quite nice work. But it will probably get caught by ETW, because in some applications, you don't need to put a strong hardware breakpoint on execution. It may look weird. When we use hardware breakpoints, we mostly use these three functions. We basically use getThreadContext, because we're going to execute our shellcode on a thread. We can have the maximum number of 4 breakpoints per thread. When we exceed this number, we're not going to set a breakpoint, and in general, things will go wrong. Then we use setThreadContext to basically create a new breakpoint, as we already mentioned, with the limitation of a maximum of 4. And finally, NT-continue when we are able to change all the required addresses, find the required DLLs, etc. Direct syscalls. If you have played even a little bit with Cobalt Strike, you probably have seen this option. Do you want your implant to have direct syscalls? Basically, no, because this is a very old technique and it's not evasive at all. I just put it here for culture, I guess. As we have already mentioned, we have the 4 magic instructions where we store RCX to R10, for example. It's not mandatory to use R10. It's mostly like a common paradigm to play with. Then we store the SSN, the syscall service number. Yes, I remembered it. To the EAX, perform the syscall, return to normal malware execution. Also, we have this very cute, I would say, diagram, where it is basically the flow of a malware. We're going to allocate some space, write on this virtual memory, we're going to write our cell code, which is basically cell code for Cobalt Strike, Sliver, or any kind of C2 reversal that we use. And if you're way too advanced, we can write custom cell code. Why not? Then we're going to create thread X, executable, and create a remote thread to another process, or even thread. We can have threads on threads. And finally, we have, OK, anti-wait for single object to return to our main program and malware. The EDR will catch us. Not EDR, basically, ETW. Why, though? Here, we have a simple dropper with Windows Win API, not native API. And we're not going to use direct syscalls or anything fancy. What do you see here? Everything moves and comes from normal DLLs. This can be kernel-based or anti-DLL. That's the intended way for an application to execute. But we have our chaos now with the direct syscalls. What do you see here? Everything is inside our malware because we use the golden instructions. And that's why, we also have this example of execution where in Notepad, once again, I named it malware for no apparent reason. In Notepad, we directly execute the golden instructions and literally bypass all the other parts of importing a DLL, calling a function, and then it makes the call stack look really bad. Can we fix the situation? Of course. We have indirect syscalls, the Toyota Corolla of malware development. It is old, stable, reliable, and it basically works. It gets you from no access to an initial beacon. What's the cool part about indirect syscalls? Basically, we do the exact same process, but instead of using directly the 4 golden instructions, what are we going to do? We're going to move RCX to R10, put the syscall number to EAX, but see a small difference? We're not going to perform a syscall. We're going to jump directly into anti-DLL, probably a clean copy of anti-DLL. For example, we can use anti-DLL refresh, let's say. And we're going to call syscall and ret from the part of the function that belongs to anti-DLL. So our call stack will look way better. It's like ROP, return-oriented programming. Does anyone here play binary exploitation or Pwn? 1, 2, wow. Well, basically in binary exploitation, you can use ROP chains and ROP or JOP, return-oriented programming, jump-oriented programming, and move on the binary however you want. That's what we basically do here, where we have everything ready, and then we literally jump to syscall and ret from anti-DLL. Let's have a small comparison here. This diagram uses Windows API, and the other one uses indirect syscalls. We're literally doing the exact same thing, but the only difference is how we call it. This one will get caught probably at virtual alloc, on the first call. The indirect syscall one may or may not get caught. Okay, we're going to talk now about indirect syscalls versus ASLR. Do we all know what ASLR is? I see very few people. So basically ASLR, what it does, it takes a DLL and it like scrambles the address that all the functions are imported. So we cannot like directly communicate with the DLL. To avoid such issues, we're going to get the base address of NTDLL. That's like our crown jewel in malware development. Then we're going to add the offset of the function and syscall that we want to call as a gadget of some sort, and voila, we have our syscall completed. Now, in this example, we have the chaos of direct syscalls. As you see, everything is inside the malware. And then we have the beauty of indirect syscalls. Everything is as intended. We have NTDLL, kernel base, everything perfect, right? Now, we're going to talk about the main ETW bypasses. The first two, I think, are related to the driver trick, where I'm going to explain what a driver trick is. First things first, the driver trick is loading a vulnerable driver to the system and then basically hijack some DLLs. It will literally blind the EDR on reboot because our malicious DLL is going to execute on ring 1 or ring 2, depending on the driver, where the EDR has like limited visibility there. Because, okay, we cannot like patch drivers and kernels, etc. using EDRs. We can also use tools like CLighter to spoof a Microsoft signature for our malicious and vulnerable driver. Finally, we can disable ETW as local admin. Don't do it. It's not evasive at all. Then we can unhook DLL to make logging more obscure, but once again, we will have issues with like the SOC. And my favorite part, this technique, the patching, it's also quite new, but it may or may not get detected depending on the EDR. We're going to patch in memory the entire ETW library. Let's talk about memory patching and the chaos that it's, well, basically it's not chaos, it's quite interesting. We have, once again, the normal malware flow, we set variables, we include headers, everything good, right? I hope so. Then the next step is to check if an imported function is an ETW function. ETW functions are known, anyone can use them because multiple applications in Windows can like have some logging functionality via ETW, which can be used not only for like malware detection, it can also be used for debugging purposes. We check basically if the next function is an ETW function. Then we're going to change the memory protection of the next function, the ETW function, and replace the first few bytes with a ret instruction. Well, basically, the ETW function is called, nothing is executed, we have just a ret, back to our malware. And finally, okay, we have the execution of our intended function. For example, virtual alloc or NT-allocate virtual memory. We use, once again, these three functions, get process address to like get the address of the ETW processes in order to check the next call. Dynamically, by the way. We change the memory permissions with NT-protect. And finally, we have NT-write virtual memory to replace the first few bytes with the ret instruction. Someone may say that, okay, this is going to corrupt like the entire syscall. No. It may corrupt it, but we actually don't care. We're literally on a ret. Ret is executed, we're back on our malware, we're happy. So we're going to have some EDR fun facts where basically we can spawn a suspended process and the EDR will not place hooks. We have already talked about it on the DLL refresh section. And finally, some EDRs may be blinded with the driver trick. Well, it was nice to be here, and I'm sure that you are probably tired from listening to me saying about C++, EDRs, and all that geeky, nerdy stuff, right? And I'm sure that you will probably enjoy some dwarf metal. I really want to do. So, are there any questions?